All right, class. We're going to be talking today about spread footing design. So here's, without further ado, jump right into our lesson. So when we talk about spread footing, we're really looking at the final portion of the foundation that kind of connects your building to the actual ground around it, to the soil. And so that's the final calculation here in the structural analysis unit. So spread column, as mentioned, we have all the load coming from the beam, girders, columns. Comes down into the foundation here. So in this case, it's kind of a pier and made out of some sort of concrete or masonry. And then finally, it has your spread footing. So it kind of spreads out the load into the soil. Okay, so it's kind of the widened portion of the foundation. And we designed this based on the soil that's around the structure, as well as obviously how much load that column has to take. So following this down, we're kind of chasing the loads again. Starts off from the very top, from the roof, down to the column, into whatever the second floor loads might be. That could include the weight of the column itself as well. And that kind of goes down into the first floor, all those whatever loads there, live loads and dead loads, again, into the foundation itself, and then finally into the footing, which leads into the soil. All right, so this depends on the total load. That part's obvious. So how heavy the building is, what kind of furniture, appliances, things like that are going to be in the structure. And then it's also, as mentioned, based on the soil bearing capacity. So the soil itself, there's kind of a table that I'll show you shortly that kind of keeps track of what different types of soil are able to handle. All right, and here's the equation that we'll be using quite a bit today. It's a simple equation, but we'll kind of see where these numbers come from. So the value Q refers to the soil bearing pressure. And then on top, we have the load applied P, that would typically in pounds. And then the A, the area of the footing, that would be typically in feet squared or square feet. So meaning that the units for soil bearing pressure should be in pounds per square foot. All right, as mentioned earlier, here are some of the different soil types. These are the most common ones that we'll be thinking about, and the allowable soil bearing pressure as shown there in pounds per square foot. So you can see that the bedrock is the best at soil bearing, and so they have values anywhere between 4,000 and 12,000. But the trade-off is it has poor drainage. So we talked about a little about how there's flood loads, or in a little bit later we'll talk about stormwater runoff as well. Okay, and that leads us to things like gravels and sand with fines in there. And so they have slightly different soil bearing, but while they also have good drainage. And that gets into their silts and the clays, which are, again, not very good at soil bearing, and they're just decent at drainage. And then the organics are not really good at either. And thinking about swampy areas, they don't hold well and they drain poorly. The worst of both worlds. All right, so here's getting into some calculations. We're going to try to get the allowable bearing pressure to be greater than the amount of pressure that's actually present. And so that's rearranging this equation a little bit. Oftentimes we're going to try to solve for, or meaning that the design of our footing is going to be the area of the footing is going to be the load, which is P, over the allowable soil bearing pressure. Okay. Now this value here is really talking about, typically our footings are going to be made out of concrete. And so this is actually the density for concrete, pounds per cubic foot. And simple calculation, we're always going to use that 150 value as long as it's concrete. And we'll multiply it by T, the thickness of the footing. And that will give us the allowable pressure of the footing. Okay, so typically we'll find the total value of the soil bearing pressure is going to be the allowable minus the bearing pressure of the footing itself to give you the total value here, the Q net. Okay, and so again, one more time, there's your equation. So we want the area to always be greater than the load of the column divided by the allowable soil pressure. All right, let's do an example. So we got example column B3. So it's labeled right there on our diagram. And that is, as you know, an interior column. So we're already told a couple things. The thickness of the footing is 1 foot and 9 inches. And oftentimes when we do this, you notice that we always want to keep our units constant. So I would actually turn this into 9 inches is this equivalent to 3/4 of a foot. So this would be 1.75 feet. Assume that the footings bear on silty sand with an allowable soil bearing pressure of 3,000 pounds per square foot. So we're going to want to keep track of these numbers. This is us kind of chasing the loads again. So it goes down from the girders, the beams, into the column, and finally into the footing. Here's a top-down view or kind of a floor framing view of that column. Again, noticing it is an interior beam. If we were to go back to a few lessons ago where we talked about chasing loads and kind of what loads are present on a given column, this is what we'd have to do. Okay, but there's been some work done for us here. So already done some analysis. We found that the roof beam reaction force is 5,000 pounds. The girder reaction force is 10,000. On the second floor, the beam reaction force is 13,500. And then the girder on the second floor is giving us 27,000 pounds. So we're going to use these numbers. Essentially, we're going to add all these numbers together, get one load to see what the column load is. So adding these together, we have the roof first. So since there's beams on both sides of that column, it's an interior one. If it's exterior, then we could just use one. So since there's 2 on either side, we'll have 5,000 times 2 gives us 10,000. Same with the girders, there's 2 on each side. So we take that value times 2 gives us 20,000. On the second floor, again, there's 2 of them since it's an interior beam. So 13,500 times 2 gives us 27,000. And then the girder, same thing, 27,000 times 2 gives us 54,000. Add all those numbers together. Oh, also include the weight of the column itself, which was 1,500 pounds. And our total column load is going to be 112,500 pounds. Okay, so that's going to be our value P. Coming back, doing a couple more calculations here. We need to figure out what's the soil bearing pressure of the footing itself. So that's based on the thickness of the footing. Remember in the question, it said 1 foot 1 foot 9 inches, so which would be 1.75 feet. Simply take that number, multiply it by 150. This is the density of concrete, gives us 262.5 pounds per square foot. All right, and to find the total allowable soil pressure is the 3,000 pounds per square foot. That's given from the table. So just to look back here, sorry, scroll all the way back to the question. We were told that this is on silty sand with an allowable soil bearing pressure of 3,000. So that's where that number came from. Or we could have looked that number up. Okay, scrolling back all the way down back to where we were, sorry. So here we go, 3,000 minus that 262.5. This is what the footing is able to take. And that gives us a total allowable soil bearing pressure of 2,737.5 pounds per square foot. Putting that into our equation, the total column load was what when we added up all those numbers, got 112,500. Divide that by the allowable soil bearing pressure, and that gives us the total area that that footing needs in order to properly hold up the structure. Okay, so we need an area of at least 41.1 square feet. Okay, at that point, then it's just kind of choosing shapes and what makes the most sense. For us, we'll often see square shapes just because it's relatively balanced that way. So we'll easiest would be take the area, take the square root of that area, and that'll give us what each side of the square would be. Obviously, sometimes we'll see rectangular shapes. Sometimes these are useful, especially if we're going to add on to a pre-existing footing. Then we might make a rectangular shape where we just kind of add to the sides. And then finally, we have your circular shape is also fairly common. So you find whatever area you have, divide it by pi, take the square root, and that'll give you the radius that you need for the circle. Okay, so we'll start off with the square footing. So if we wanted a square footing, then we would take that value that we found just now, 41.1 square feet. And as I mentioned, we'll take the square root of that. So each side needs to be at least 6.4 feet. And typically we'll round that up to the closest 3 inches, right? So some factor of 369 or a foot. So in this case, we round that up to 6.5 feet. So it'll be 6.5 on each side. The thickness was given. Okay, so that would be one valid option for your footing. The other one, if we went with the circle approach, then we take 41.1 square feet from that calculation we did earlier, divide it by pi, gives it 13.1, take the square root. So the radius would need to be at least 3.6 feet. And like I said, we always round it up 3 inches or to the closest 3 inches. So we'll go to 3 foot 9 inch radius. Okay. And then in terms of diameter, we'd say 7 foot 6 inches. Again, the same thickness as what was given in the problem. Okay. Any questions here? If you do, please feel free to send me a message here, or obviously you can ask me.